Okay, so let's talk about halogenation and things that we can predict just from other things that we already know. So thermodynamic considerations, all right? So if we want to determine whether a process is going to be favored or not, we have to determine the sign of delta G. Is it going to be spontaneous or not, right? So if in a halogenation reaction, the entropy term is negligible because we start out with, 2 moles of reactants and 2 moles of products, right? And so therefore, since this term is basically negligible, it's not zero, of course, but it's negligible, then we can say that if we understand the change in enthalpy, we can basically make a prediction about whether or not the process is going to be spontaneous, right? It's going to happen or not. All right, so let's look at the bond dissociation energies. Now, the bond dissociation energies for that bond right there are all the same, of course. But if we're talking about a fluorine-fluorine, then it's 159. These are the bonds that have to be broken in order to fluorinate, right? And these are the bonds that are formed if we're going to fluorinate. Or halogenate, right? Right. In this case, it's these here, right? And these here. So in order for us to find out the change in enthalpy, we take the difference between the bonds broken and the bonds formed. All right, so that being said, we find out that for fluorination, it is very exothermic, very exothermic. With chlorination, it is also still pretty exothermic, not nearly as bad as 431. Look at that, 431. Okay, so for chlorination, it's only 104 kilojoules per mole. Bromination, still exothermic, but not nearly as much. Okay, and iodination is actually endothermic. Okay, so this is not going to happen. Iodine's not going to happen because it's endothermic, right? So fluorination is violent, and so consequently it's not useful to us. Iodination is not thermodynamically favored, so it's not going to happen. Only halogenation with chlorine and bromine are useful. Now, chlorination is still pretty exothermic, okay? Now, it turns out that they're both exothermic in terms of net, right? Look at that. There's the net exothermicity. But the first step, that's the initiation with bromine, is actually endothermic. So since this first step is endothermic, then that means that bromination is going to be a lot slower. Let's look at that from an energetic standpoint. So here's my first step. Like so, for chlorine, you can see it's actually going down, right? But for bromine, it's actually going up. Okay. So since it's endothermic, that first step is endothermic, and this activation energy is really high. You see that activation energy is really high. Activation energy. That means this is going to be very slow. Since it's slow, that means that we can control it. That is nice, okay? Now, I mean, just by the energy diagram itself, we don't have any numbers on there. You can't tell how slow that is. A lot of times when I say it's really slow, what we mean is, well, this is so slow, it's never going to happen. It turns out this is slow, but remember, it's exothermic. And so, and it turns out that activation energy is something that we do have enough energy to give it. So we can do bromination. We're going to preferentially do bromination. Chlorination is only for extreme circumstances because it's just too fast.